Right, okay, so due to popular demand, I've moved it back onto the video camera versions to support the needs of whatever, to support your needs. So in this video we're going to look at Kirchoff's second law. So Kirchoff's second law, and this goes along with the potential difference in voltage video that was done on the iPad version. But Kirchoff's second law is to do with the idea of conservation of energy. So Kirchoff's second law is all to do with conservation of energy. And we'll talk more about that concept in a second. Whereas in Kirchoff's first law, with the current splitting and whatnot, that was all to do with conservation of charge. So this law is to do with conservation of energy, that law was to do with conservation of charge. So how do we conserve energy in a circuit? Well, the source of energy in a circuit is generally the movement of those electrons around the circuit carrying an amount of energy per unit charge. Because as we defined before, voltage is an amount of energy per unit charge. And we were quite happy with that in the previous video without too much difficulty there. So this is all to do with the amount of conservation of energy. So as with Kirchoff's first law, second law is exactly the same. The second law is all about what you put in is what you get out. Now I know I said that in the first video about Kirchoff's first law, but it's the same thing here, just in a different way. So let's draw our circuit. We'll have a power supply of 6 volts, and we'll bring it round to a resistor, fixed resistor, like that. Okay, and if we were to attach our voltmeter in parallel across that resistor, what voltage do you think we'd expect to get out? Well, as I already suggested, what you put in is what you get out. So in this case, we're putting in 6 volts of energy. And so what we're going to be getting out as a result is 6 volts. So we're going to be seeing that voltmeter read 6 volts there without too much difficulty. So where do we go for next with this? Well, we can see what happens when we add another resistor in series with this one. So we add 2 resistors now. And we'll talk more about resistance and the concept of resistance when we talk about Ohm's law and resistors in more detail. But the point is that what you put in is what you get out. So say, for example, I have a voltmeter and this one reads 4 volts. So what I put in is what I get out. So what am I not getting out so far? Well, hopefully you're seeing I'm putting 6 volts in, I'm getting out 4, so therefore there should be a voltage of 2 volts across that one. Because 2 and 4 are what I'm getting out, 6 is what I'm putting in, and so as a result, in that loop, we have conservation of energy. But, as you well know, we don't just put voltage in, we don't just put resistors in series, we can also put them in parallel. So what happens when we put one in parallel? So we've got one there, we've got our original one, and we've got another one there. So, now you might expect something similar to happen here. So if we've got a circuit where we've got a voltmeter attached there, and we have a voltmeter attached here, how would we expect the voltage to split if, say for example, both of these resistors are identical? So some of you might be saying, oh, well, surely it will share the voltage between the two. Unfortunately, you couldn't be further from the truth. If you set this circuit up, and you will do, you will observe that the voltage here, we'll call this voltage 1 and this voltage 2, we will observe that voltage 1 here will be equal to 6 volts. So what would V2 be equal to? Well, I guess that must be 0. No, it's also 6 volts. How can that be? How can that be? That doesn't make any sense, surely, because if I'm putting 6 volts in, how am I getting 6 volts out across this resistor and 6 volts out across this resistor? Conservation of energy is implying, how can this be right? Well, it is because when you think about the concept of what's going on inside the wire, Think about an electron travelling from, let's say, the negative terminal towards the positive. So here's my electron travelling round, being pushed, and he comes to that junction and he goes, which way do I go? Well, he can either go that way or he can go that way. And as you would expect, it's not just one electron travelling around this circuit. There's loads, there's billions of them travelling all around, being pushed through that circuit. And so approximately half of the electrons would go this way and half of the electrons would go this way if these two resistors were exactly identical. And so what we end up having is we get the electrons travelling through this resistor and the electrons travelling through this resistor. They all have the same amount of energy per unit charge. Remember, let's go back to voltage is amount of energy per unit charge. Electrons have a very specific amount of charge, so they have a specific amount of energy based on this equation. So if they have a specific amount of energy per unit charge, then all of those electrons, the ones here and the ones here, have the same amount of energy. And so as a result, when they travel through that resistor, they dissipate that energy. They do work as they travel through the resistor, and as a result, they come out the other side with all their energy used up, and then they'll travel back to the power supply to gain that energy back again. Same thing here. They'll travel all the way back to get that energy back again and start the journey all over again. So in terms of that, that's the concept that we're looking for there. So in the next video, what we'll do is we'll look at the next section and we will move on and we'll have a look at some more advanced versions in the next video.